Okay, so you know how to analyze a bond. Now you know how to analyze a whole molecule for being polar or nonpolar. Next, we're going to talk about how does being polar or nonpolar cause molecules to interact with each other. All right, this will take us to boxes 6 and 7 on the Unit 9 Polarity Hyperdoc. Okay, this is all about IMFs. We've heard the term IMF before. It means intermolecular forces. Okay, here I've got 3 HCl molecules. An HCl is a polar molecule. It has kind of a positive end and kind of a negative end. Okay, but now let's look over here within this HCl. The hydrogen and the chlorine are held together by a bond. A bond is an intramolecular attraction. Inside a molecule, there is a bond that holds the hydrogen and the chlorine together. Overall, this molecule has kind of a negative end and kind of a positive end. What that means is these molecules are attracted to each other by intermolecular attractions or intermolecular forces. IMFs, or intermolecular forces, are attractions between molecules. They happen because certain molecules have one end that's positive and one end that's negative. IMFs can be weak, and they can be strong, they can be medium, and we're going to talk about that next. The weakest, there are 3 kinds of IMFs, okay? Weak, medium, and very strong. The weakest IMFs are between nonpolar molecules. The weird thing here is these nonpolar molecules, they shouldn't even attract each other. They don't have a negative end and a positive end. There's no reason for them to be attracted to each other like little magnets. But because molecules are weird, they attract each other a tiny little bit. When molecules get near each other, they basically induce a dipole in each other and they get a little bit attracted to each other. Don't worry about it, it's weird, but just nonpolar molecules shouldn't attract, but they do. They attract a tiny little bit. And these weird, weak IMFs are called van der Waals forces. Okay? The weakest IMFs are between nonpolar molecules that shouldn't even attract each other, but they do. Okay, medium IMFs. This makes sense. If we have polar molecules, molecules that have a positive end and a negative end, like these HCl molecules, or like this SH2 molecule, it should remind you a little bit of a water molecule. It has a negative end and a positive end, a negative end and a positive end. Polar molecules should attract each other because they have opposite charges on either end. The positive attracts the negative to their molecules that are nearby. Okay? This should make sense. Medium strength IMFs between polar molecules, and since each molecule is a dipole, it has a positive end and a negative end. Okay? There's the dipole there. Here the dipole would kind of be like this. Okay? These are medium strength IMFs. They're called dipole-dipole forces because you've got something with a positive and a negative that's being stuck together by the idea of opposites attract. Okay? Dipole-dipole forces are the medium IMFs. Okay, now the special strongest IMFs. The strongest IMFs are called hydrogen bonding. This name is very confusing, but you will get it. Okay, hydrogen bonding, you have to have hydrogen. Okay, hydrogen bonding it's not the bond inside the molecule that holds the hydrogen to the oxygen. It's the attractions between these molecules. Okay, and the hydrogen bonding is not inside these water molecules. It is the attractions between the water molecules. And in this case, with hydrogen fluoride, HF, the hydrogen bonding is the IMFs or the attractions between the molecules. It's not the bond of the hydrogen in the molecule. That's why this name is confusing. Anyway, hydrogen bonding only happens if you have a molecule that has hydrogen attached to F, fluorine, O, oxygen, or N, nitrogen. Then there's hydrogen bonding. It's that easy. Mr. Young, how will I remember that? Okay, in the 80s, there was a weird movie about a cute or sort of cute alien named E.T. E.T.'s catchphrase was, E.T. phone home, because E.T. wanted to get home. If you remember E.T. phone home and you spell it F-O-N, okay, that will help you remember that hydrogen bonding happens when you have hydrogen bonded with a nitrogen, bonded with an oxygen, or bonded with a fluorine, okay? So if hydrogen is with nitrogen, hydrogen is with oxygen, hydrogen is with fluorine, there will be hydrogen bonding, okay? So a molecule like NH3, does it have hydrogen bonding? Well, let's see, ET phone home. Yeah, it has hydrogen with nitrogen. Yes, NH3 will have hydrogen bonding. It will have very strong IMFs. Same with HF, same with H2O. Those are three molecules that have very strong hydrogen bonding. So overall, hydrogen bonding is really kind of cool. It's the strongest IMF. Okay? Hydrogen bonding causes water to have a very high boiling point compared to similar molecules. Hydrogen bonding gives water its very strong surface tension. All these water molecules sticking together basically gives water a skin at the surface, and that's how a bug like this water strider can walk on water. Okay? Hydrogen bonding also makes water droplets bead up like this. They have this high surface tension that gives them sort of a skin, just like on the surface of the water with the water strider. It also makes ice have a weird density. Hydrogen bonding has all sorts of interesting effects. Remember, it's the strongest kind of IMF, and you can figure out if something has hydrogen bonding using the ET phone home mnemonic. All right, so this must be really important. Remember, hydrogen bonding makes water special. Any questions that ask about why does water have a high melting point? Why does water have a high boiling point? Why does water have this special surface tension? The answer is going to be because of hydrogen bonding. Okay? All right, finally, wrapping up IMFs, here we go. There are weak IMFs. Those are called van der Waals forces. They shouldn't even exist because nonpolar molecules shouldn't really attract each other, but they do. They have this weak little attraction. Those are the weakest kind of IMFs. The medium strong IMFs are between molecules that are dipoles. They have a positive end and they have a negative end. These medium strong IMFs are called dipole-dipole forces, or dipole-dipole IMFs. And you have to have polar molecules for that to happen. And they attract each other with a medium amount of intermolecular force. Finally, the super strong IMFs are when you have hydrogen bonding. Okay? Hydrogen bonding, if you have hydrogen with fluorine, oxygen, or nitrogen, it will have a very strong polarity in the molecule, and that means that you get this really strong attraction between the molecules. But it only happens if you have HF in your molecule, HO in your molecule, or HN in your molecule. Then you have hydrogen bonding, the strongest kind of IMF. Here's an important bonus fact. Let's look at these two molecules. They're both nonpolar, okay? You could fold this octane, the top one, in two directions. It has two axes of symmetry, so it's nonpolar. And same with the pentane. You could fold it in half vertically, fold it in half horizontally. It's a nonpolar molecule. But these two will have different IMFs. It turns out longer or larger molecules have stronger IMFs. The longer octane molecule, it's easier for it to get tangled up and stuck to other octane molecules because it's longer and bigger. That basically gives it stronger IMFs. Pentane is a little shorter. It's not quite as sticky to the other pentane molecules as octane is to octane molecules. So longer and larger molecules have higher melting point and higher boiling point. Let's look at the boiling points and melting points because there's a little tricky thing here. Okay, octane has stronger IMFs, so yes, that boiling point is higher. Now let's look at these melting points. This is a negative number on the Celsius scale. Octane has stronger IMFs. It should have a higher melting point. Minus 57 is a higher temperature than minus 130. I see students make a mistake with this all the time. Remember, on a number line with negative numbers, a larger negative number like minus 130, that's lower than a number like 157. Than negative 57. Negative 57 is a higher melting point than negative 130. Think about what a number line looks like. The larger negative number is lower on the number line. You may be saying, Mr. Young, that's really obvious. I see students make mistakes with that all the time with negative temperature numbers. Okay, it should now be pretty easy for you to cruise through the activities in box 6, and then box 7 will take you through a bunch of practice activities of all the concepts in Unit 9, in the Polarity unit. Okay? Thank you for watching.